we're going to take a look at a new topic that we've touched on before, but we're going to go a little bit more in depth. We're going to talk about the Death Star. No, I mean the death of a star. Death of a star. How does a star die? Of course, if you want to know when a star is going to die, you need to know its mass. Bigger stars are going to have shorter lives, smaller stars are going to have longer lives, and it all depends, as almost everything else does, on the star's initial mass. There's actually a really simple equation to figure out about how long a star is going to last. It's 1 divided by the mass raised to the 2.5, where the mass is in solar masses. So the sun would be a 1. If you have a star with a solar mass that is half the size of our If you have a star with a mass that is half that of our sun, it's going to last between 60 65 billion years. Because it's such a much smaller star, it's going to last a very long time. It does not burn through its fuel that fast. However, if you have a huge star, an O-class star, that is 20 times bigger than our sun, it's only going to last for a couple million years. And you might think a bigger star should have more fuel, it should last much longer, but because it's so big, the fusion is going so incredibly fast that it burns through that extra fuel very quickly. It'd be similar to having something like a dragster, those cars that go like a quarter mile, versus, I don't know, like a Honda Civic. The Honda Civic has less gasoline in it, but it can go farther than a quarter mile. The bigger car is going to burn through its fuel much faster. The bigger star is going to burn through its fuel much faster. So let's figure out how stars die. We've mentioned the 3 ways: planetary nebula and a white dwarf, a neutron star, and a black hole. Let's look at that a little bit more in depth. Those 3 possible endings have to do with the mass of the core of the star. So this whole time I've been talking about the overall mass of a star, and that does have an effect because a bigger mass star is going to have more mass at the core. And remember, the core is where fusion is happening. So if you have a huge core, you're doing a lot of fusion, but it is the core of that star that's going to affect what happens after the star dies. If you have the core of a star and the core is 1.4 solar masses or under, it's going to turn into a planetary nebula and a white dwarf. This 1.4 right here is what's known as the Chandrasekhar limit. Chandrasekhar was an Indian American astronomer who died about 25 years ago or so, but he calculated what pressure you would need to have in order for a supernova to happen. And he figured out that if you have a core that is smaller than 1.4 solar masses, there's not enough pressure for a supernova. However, if you have a core that is more than 1.4 solar masses, so 1.4 is this magic Chandrasekhar limit. If you have a core that is more than 1.4 solar masses, well, then you're going to be able to go supernova. So if you are between about 1.4 and 4.5 to 5 solar masses in your core, not the overall star, just in your core, you're going to go supernova and end up as a neutron star. We will get to neutron stars in a day or two. However, if you have a core with more than 5 solar masses, and these are the huge, huge stars that are like 20, 30, 40 times bigger than the sun themselves, the core itself is going to be 5 times bigger. You're going to go supernova and end up as a black hole. We'll get to black holes as well and what all of this means, but we're going to focus today on this top one. If you have a core mass 1.4 suns or smaller, you're going to end up as a white dwarf. If we were to make all of these objects to scale, our sun would be about 38 yards, or, think of a football field. From the goal line to the 38-yard line, that would be the sun. The core of a small star is only about a foot across, about the size of a volleyball or a soccer ball or a basketball. So take a basketball and put it on a football field, and then compare it to, 38 yards. That is how small a white dwarf is compared to our sun. A neutron star, this is life size. It would be a dot. And a black hole would even be a smaller dot. There are some supermassive black holes at the center of galaxies that are bigger than our sun, but these black holes that happen after a star dies are really tiny. Betelgeuse, that red giant that's over in Orion in his shoulder, going to go supernova at any point, just to scale would be 22 miles if the sun was 38 yards. Betelgeuse is huge. So these objects that are going to happen when a star dies are pretty small compared to stars. White dwarfs would be a foot across, and then neutron stars and black holes are just a little dot if the sun was 38 yards. Inside of the core of our sun, it's doing fusion. It's on the main sequence, turning hydrogen into helium. When it runs out of hydrogen, it's going to take helium atoms and start smashing them together. It's going to cause more energy to be pushed out. The sun's going to expand out. That helium is being turned into carbon. So in the core of a red giant star, carbon is being made under extraordinarily huge amounts of pressure. What do you get if you take a bunch of carbon and put it under huge amounts of pressure? You get a diamond. So a white dwarf, which is made out of carbon and the size of a planet with a ton of pressure, are basically diamonds the size of Earth. Now these diamonds the size of Earth are many millions of degrees hot. You couldn't go there. The amount of X-ray radiation would kill anybody that tried to get close. They're too far away to get to anyways. But it's kind of fun to think that white dwarfs are really nothing more than planet-sized diamonds. So what exactly is inside of a white dwarf? Well, we just mentioned that in a normal star, you're taking hydrogen and smashing it together to make helium. And when you run out of hydrogen, you start smashing helium together to make carbon. But what happens when you run out of helium? When you run out of helium, you don't have anything else that you can smash together. There's not enough pressure to smash carbon together. So gravity is pushing things in, but not with enough pressure to cause carbon fusion, which means gravity is going to start to win. And it's going to take all of that helium that's left over, and it's going to start pushing it and compressing it. And eventually, gravity is going to keep making it smaller and smaller until the only thing pushing back is the electron degeneracy pressure. If you have more than 1.4 solar masses, then there is enough mass to push past electron degeneracy pressure. If you have 1.4 solar masses or less, you have electron degeneracy pressure pushing back against all of that gravity. White dwarfs are obviously very hot because they are the core of stars. It's pretty hot in the core of a star, and these are leftover cores, so they are going to have a lot of residual heat. And over an extraordinarily long time, they're going to cool down into a black dwarf. Not a single one of those exists yet, though. The universe is not old enough. Back to electron degeneracy pressure real quick. Here is a helium atom. You have 2 protons, you have a neutron, 2 electrons, and those electrons from gravity have been pushed into the ground state. So far, so good. Now gravity is going to take this helium atom right here, and it's going to push it right up against every other helium atom that it can find. Normally you would have a gas, and these electrons could be in different energy levels. But because of the immense gravity, it's going to take all of those electrons, push them to the ground state, then take all of those atoms and push them right next to each other, so that the only thing keeping these atoms apart from one another are the fact that electrons hate being around other electrons. And it's the electrons and that electromagnetic negative hating and negative that's pushing apart, just like a magnet would. That is the only thing keeping these from getting any closer. Gravity wants them to get closer. Gravity wants to keep smushing them down. And the only reason that they don't get closer is because of these electrons, which are then pushing back out against gravity. This is why it's called electron degeneracy pressure. It has degenerated all the way down to the point where only electrons are able to counteract against gravity. There's no fusion to push out. It's just the negative charge of the electrons pushing back out against gravity. That is electron degeneracy pressure. Let's figure out how weird these white dwarfs are.
Humans can survive in this universe as long as we have an energy source. Unfortunately, the universe will die. It will happen slowly, over many billions of years, but it will happen. On a universal timescale, stars like our Sun will be gone in no time. Luckily, there are places that will exist practically forever from a human perspective. The corpses of dead stars. White dwarfs. They could be humanity's last home right before the death of the universe. What are these strange things? And what happens when they finally die? How long stars live varies drastically, depending on how massive they are. For example, really massive stars burn hot and fast, dying violently in supernova a few million years after birth. But they're the exception. 97% of all stars will end their existence as white dwarfs. There are two ways this can happen. Small stars, so-called red dwarfs, burn out over trillions of years until they eventually quietly turn into white dwarfs. Medium-sized stars like our Sun are more interesting. Imagine the Sun as a huge pressure cooker that fuses hydrogen into helium in its core through its gravity. The fusion of elements releases extreme amounts of energy that pushes outwards and stabilizes the star, keeping it in a delicate balance. When the Sun is old, the hydrogen in the core is exhausted, and the Sun will begin to burn helium into heavier elements. While doing so, it will shed its outer layers. When this process is over, more than half of the Sun's mass will be lost into space as a spectacular planetary nebula millions of kilometers across. What remains will be its former core. A white dwarf is born, a star corpse. While its former self was about 100 times its diameter, now it's only about as big as Earth, but still with about half of its former mass. This means it's extremely dense. A teaspoon of white dwarf is about as massive as a car. Its surface gravity is over 100,000 times higher than Earth's. If you tried to land on it, you'd immediately be compressed into a steaming puddle. Life around a white dwarf is very unlikely, but possible. Most of them that exist now were former stars that, well, died, which probably ruined any planets they once had. But that's not all. Since they are so small, a planet would need to orbit them about 75 times closer than Earth is to the Sun to have liquid water. This proximity has up and downsides. For one, it would tidally lock the planet, giving it a permanent day and permanent night. At the edges of these day and night zones, life could be possible. But white dwarfs have a very stable energy output, so they might actually be safer to live around than many red dwarfs. This is still speculation at this point, but if we could find a white dwarf with the right conditions to settle around, we could have a home for many billions of years. But why do they shine so much longer than other star types? White dwarfs are very, very hot, up to 40 times hotter than our Sun, ranking among the hottest objects in the universe. But they are not incredibly active. All the heat inside of them is trapped and has nowhere to go. Only on its outer layer can it escape into space. But space is mostly empty, so heat can't be transferred by conduction. The only way energy can escape is by radiation. This is so inefficient that white dwarfs will take trillions of years to cool down, which may make them humanity's last refuge. They might be the last sources of light and energy in a dying universe. According to some estimates, white dwarfs might shine as long as 100 billion years. 10 billion times longer than the universe has existed. So far into the future that no regular stars will shine anymore. Galaxies will have evaporated. And only then will the first white dwarf turn into the first black dwarf. When this happens, the last hope for life will die off. Black dwarfs will be inactive spheres with no energy left to give. Still massive enough to kill you if you get too close. So cold that they'll be near the coldest possible temperature in the universe. So dark that they are practically invisible. The universe will enter its last stage, heat death, which will leave the universe unrecognizable. An absolutely dark and cold graveyard with black holes and black dwarfs scattered over trillions of light years. We don't know for sure what will happen with black dwarfs in the end. If the proton, one of the fundamental parts of atoms, has a limited lifespan, black dwarfs will slowly evaporate over many trillions of years. If the proton does not decay, black dwarfs will probably turn into spheres of pure iron via quantum tunneling over a time span so obscenely gigantic that calling it forever is okay. These iron spheres will then travel completely alone through a dark universe. Nothing new will happen anymore. Forever. While this may sound kind of dark, this is so far away that for our purposes today, it might as well not happen at all. It doesn't matter what happens in a billion trillion years. Right now, we happen to exist at an excellent time, able to be in awe about a universe filled with endless stars and light and planets, and enough time to visit them one day.
So the core of a star turns into a white dwarf. What happens to the rest of it? The rest of the material in that star expands out in a planetary nebula. They're basically the remnants of stellar death. They can be nice and spherical like the one over my head, or they can have all kinds of really cool shapes and super complicated structures. They're some of the coolest looking objects in space, and they all have a little white dwarf at the center because they're the outer layers of the star. At the center is going to be that core. So there's a little white dwarf in the one over my head. There's a white dwarf in this one. And they happen because as that red giant is expanding, the outer layers are so far from the center of gravity that they just drift off into space. The gravity of the star loses hold of those outer layers and they just float away. And so this is nothing more than the outer layers of the star that have started to float away from that center of gravity. Because the white dwarf in the middle is glowing in X-rays, it ionizes that outer layers of gas and it starts to glow. We get some of these cool images. They are expanding out slowly and they only last between 10 and about 40,000 years. The star is going to start to cool down when fusion turns off. They also just spread out into the universe, spread out into space, and they get so spread out and diffuse that we literally just can't see them anymore. That material is still there, it's still floating through space, but it's so spread out that it's invisible to any of our telescopes. Which means if you got into a time machine and went ahead 50,000 years, not a single planetary nebula that exists today would be visible. All of the planetary nebulas that we see now are only going to be around for a few thousand years. Why are they called planetary nebulas if they are the death of a star? They were first found back in the 1700s when they did not have the greatest telescopes. And nebula, of course, means like a cloud or bunch of gas. And they thought that they looked like planets that were kind of fuzzy. And they started recording where they were located and cataloging them and said, this is planetary nebula number 1 and this is number 2. And then we realized that they have nothing to do with planets whatsoever. They have to do with stars. Instead of being smart and going back and changing the name, we just kept the name Planetary Nebulas, and now everybody just has to learn a planetary nebula is a dead star, has nothing to do with planets. A stellar nebula is a big cloud that condenses into a star. That's the beginning of a star's life. A planetary nebula is the end. It's a horrible name, nothing to do with planets, but we used to think that they looked like planets. That's where the name came from, and it stuck. But they do look super cool. There's all kinds of different shapes, all kinds of different colors. Let's just take a look at some of them. Because these objects are, in my opinion, some of the coolest objects in space. There's a bunch. There are a bunch of them, and they all look really neat. And every single one of them has a white dwarf. So here's a white dwarf, there's 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 a white... You get the idea. The center of every single planetary nebula is a white dwarf. Because here are the outer layers of the star, here's the core of the star. Sometimes astronomers get naming things completely correct. For planetary nebulas, oftentimes they're simply named after what they look like. In this case, this is called the Green Bubble Nebula. And as we zoom in and zoom in and zoom in, hopefully it will become very apparent why this is called the Green Bubble Nebula. I don't know if you guys can see it yet. It's just now starting to come into view. But the Green Bubble Nebula is named that because it looks like a green bubble. And now I want you guys to pick a nebula and learn something about it. Details on canvas.